Okay, let's do a little bit more talking about this formal reasoning with our logic. We left off in the last video looking at some weird stuff with CP and IP, right? I made all these rules and said, you know, you have to do this dash thing, right? You have to cite all these lines since the premise. And a couple of times I said, without really explaining it, we can't have used CP or IP before in the proof. And so here's kind of the scoop. When you use CP for a proof, or IP for a proof for that matter, the premise is said to be discharged, and you use all the lines starting with the premise as your reason. Okay? And why do we do that? It has to do with subproofs. So before we talk about subproofs, I want to go back to something that you're much more comfortable with, which is Java. And here's a code fragment. And I'm not trying to trick you here or anything. I'm just asking you, do you think this code fragment would compile? And, you know, kind of take a look at it. Looks pretty good to me, right? And the answer is yes, this one does compile. And if we look at it and say, what's the output? Well, we've got X and Y. X is 5, Y is 6, and Z is some double 12.4, and I print them out. So it's going to print, you know, if I run my app, X is 5, Y is 6, Z is 12.4. That looks good. Okay, no problem. Here is a little bit more interesting variant, right? Does this one compile? So let's see. So we've still got X and Y up here. And if X is less than Y, which it is, then we make a Z down here inside of this code block, right? We have a new block with an if, and we declare Z inside that code block, and we say Z gets penguin. And of course the question really that I'm asking is, can we refer to X and Y, which are in sort of this outer code block inside of our if? And of course the answer is yes, right? We can do that. And if we try to run this, it'll say X is 5, Y is 6, and Z is penguin, right? That's what it's going to print. Good. Okay, so here is what you may or may not remember from classes from a while ago, right? We can talk about when is a variable in scope. Hopefully you remember this, right? And so we talk about X and Y, and variables are usually in scope from the point of their declaration until you sort of leave the code block that they were declared in. So X and Y go into scope here, right? They're in scope, they start to be in scope, and they're in scope throughout this entire method. In contrast, Z, we only declare Z inside of this inner code block, the ifs code block. And so Z is only in scope until we leave the if. All right. And so here is my last example. And I've given it away a little bit with scope, right? Let's look at this and see what happens. So I'm declaring X and Y out here. Going into my if to declare Z, and then out here I'm trying to print X, Y, and Z. And the question is, does this compile? And hopefully you figured out that the answer is no, it doesn't compile. And so now I want to ask you, what's the error? And the error message that we get is we can't find this symbol Z, right? It says on line 34, and look at that, I left the line numbers on here so you could see, right? Variable C is undeclared. And why is that? Well, it's because Z is not in scope, right? Z was only in scope from the time it was declared until the time we left the if. And by the time we got here, we're talking about Z, but it's long gone, right? And I'm showing you this example because when we do subproofs, the subproof block is going to go out of scope. All the things that we, the premises that we made, and the and all the lines of sort of code in there that we wrote, all the logical conclusions are going to go out of scope when we leave the subproof. So what's a subproof? It's a proof that's part of another proof. Always starts with a premise and always ends by applying either CP or IP to the result. And you can only do it with CP and IP. So this is why CP and IP, well, this is one of the ways CP and IP are special. After you have exited the subproof, we say the premise is discharged, and all of the lines, all the woofs in that derivation that you had in that subproof become inactive. And what you want to think about is it's a local variable, and it goes out of scope when I leave the subproof. And we're going to indent our subproofs, and we're going to write down the result of the CP or IP outdented, right? And you just need to think about this as a code block that has super good indentation, right? We're always going to be perfect with our indentation, please, on these assignments. Super important. So I think the easiest way to understand what I'm talking about when I talk about subproofs and indentation and scope and stuff is to just show you an example. So here's a proof that happens to have a subproof in it. You know it has a subproof because there's some indentation going on here. Notice we don't indent the line numbers on the left here. We just indent part of the proof. And what are we trying to prove? We're trying to prove this woof, this whole thing is a tautology. I didn't put parentheses around this piece, but you know, since implies has a lower precedence than and, that this is actually this whole thing on the left implies B is what we're trying to prove. And since we've got this implies in there, we're thinking, maybe I can use a magical CP at the end of my proof. But don't look ahead. Let's just trace this step by step. So we start at line 1 here, right? And line 1 is just our premise, right? Whatever we're, if we want to do a CP proof, we assume the left-hand side, we derive the right-hand side, and then we do our CP. So that makes sense. Okay, so whenever we have a premise that has an and in it, we, of course, always split that up using simplification. So here's the first part. We have an A implies B and some other stuff. So A implies B, we're going to take for line 2 from line 1 with simplification. Same thing here. We get the right side of that and A or B using line 1 and simplification. Okay, and now things get interesting. We're on line 4, and what we're going to do now is I'm going to show you a little bit of a subproof. Right now I have A or B here, right? And I'm trying to prove B, right? I'm trying to start here and get to B. And this is sort of a tricky subproof. I've decided I'm going to try and do it. Well, this subproof does it using IP. So remember with IP, indirect proof, what we do is we assume the opposite of what we want to get to and hope that we get to a false. That means we have a contradiction, right? Remember, IP is like proof by contradiction. So what I'm doing here is I'm saying, okay, I'm going to start a new subproof. Think of it as like a function, a new code block, okay? And just for the purposes of this subproof, I'm making a new premise. Think of that as analogous to a new variable. I'm going to assume for a minute not B. I'm just going to assume for a minute not B. And here in our subproof, we write P just because it's a premise like we always do. But then we also, to the right of that, we put in square brackets why we did this in the subproof, right? And so I wrote for B. In other words, I'm trying to prove B, okay? So that's line 4. I'm just indenting it. I'm saying, okay, I'm going to wing it. I'm going to see what happens if I assume not B. Let's see if we can get to B. So here's line 5. Well, I can definitely figure out A. If I know, if I assume not B, then I can take the A or B and combine that with the not B and my DS rule, right? And so now I have that A is true just in my subproof here, right? And if I know A is true, and look at line 2, this is kind of weird, right? Because I started assuming not B, and now that I know A is true, I can use line 2 and line 5 together, and modus ponens, my favorite, to show that B is true. But B is false, but B is true, but B is false, but B is true. And so that lets us use the contradiction rule, right? A and not A implies false. That's not B and B. Same thing, false. So from line 4 and line 6, we use the contradiction to say false. Okay, now if this were just the end of our proof, if we weren't in a subproof, then we would write QED and all this stuff with IP, right? But we're in the subproof. And so what we're going to do is we're going to outdent, right? We're going to outdent from the subproof, and we are going to say, okay, I've proven that B is true because IP says if you assume not A and you derive false, then you can conclude A, right? So in this case, I assume not B. I got to false, so I can therefore conclude, right? If I have not B, from not B derive false, then I can conclude B. We always outdent here on the IP, and the IP gets all the lines starting with the indent premise and going all the way up to the end of that subproof, right? So it says lines 4 to 7 IP, all right? And now I have B here, so I've now proven B, right? And now, given that I have B, and remember what I was trying to do, I was trying to prove that I was trying to prove this is a tautology, right? And I was trying to do it using my CP rule, right? And my CP rule says if from A you can derive B, then A implies B. Well, we have from this, we can derive this. We just did that, right? From line 1, we derived line 8. And so now, if you just ignore this for a minute, you would have been happy writing a CP here, right? You'd have done QED because you're at the end of the proof, and you would have written CP here. And the only tricky part is what lines do you claim helped you with this, right? And the answer is that you can't use any of the lines of the subproof. Those guys are gone, right? It's like they're out of scope. And so what we're going to say is I have used CP and all the lines that are still available to me, in other words, lines 1, 2, 3, and 8, to prove that this thing up here is a tautology. Now, for me, it helps to think of the missing line number here as a kind of a virtual outdent because we used CP, right? If you use CP or IP at the end of a proof, remember, we don't put a line number, we just write QED. And I kind of think of that as equivalent to the outdent we had to do here from line 7 to line 8. We need to do another outdent from line 8 to sort of the outside end of the proof or something. I don't know how to really express it, but I find it useful to think about whenever I see a CP or an IP, I have to outdent unless I'm at the end of the of a proof, and then it's kind of a weird no number thing. Okay, so here is the proof again, just sort of shrunk down a little bit. And I want to talk, referring to this proof, I want to talk about some rules for subproofs, right? So the first rule of subproofs is you can only have a subproof if you're planning on exiting it with CP or IP. CP and IP are the only things you can have to get you out of a subproof. So only use a subproof if you think you're going to be using CP or IP, okay? For example, here is our subproof in here, and we exited it, right? We outdented with an IP, okay? When you start a subproof, you can have just one premise, and you need to write what your CP or IP exit goal is next to it. So this is, the textbook does this, and I'm also going to require you to do this. If you're ever doing a subproof, since I'm trying to prove B, and I'm going to use IP, I assume not B here, right? And so I say not B in my, is what I'm assuming is my premise, but I always put my exit goal after it if I'm in a subproof, okay? As far as CP and IP are concerned, you can only ever use CP and IP if it's the last line of a proof, or if it's the line, the outdent right after a subproof, right? And if you use CP or IP to exit a subproof, then everything in the subproof is out of scope for the rest of your proof, right? So here we used IP right after a subproof. Here we use CP on the very last line of a proof. And notice that everything in line 4 to 7 after we use that IP is out of scope for the rest of the proof. Okay, here's kind of a generic CP subproof. Okay, this is just kind of like, what does every CP subproof look like? Well, you know, maybe I have a woof that's my premise, and I have a couple more woofs that I get based on the premise, right? Maybe I use line 1, maybe I use lines 1 and 2 to get to line 3. I decide to do a subproof, right? And since this time my example is a CP subproof, I know that I'm going in here with W4 as my premise, right? My woof number 4, right? And so I know I'm going to have W4 arrow, whatever the heck it is my last thing in my subproof, as an outdent for CP here, right? So I have my woof here, my premise at the beginning of my subproof, and I have some reasons. And notice how here I'm just telling you kind of what lines you can use in your proof so far, right? So everything's in scope when you get to line 5. Everything's in scope when you get to line 6, right? Logicians would not talk about scope, right? So if you're talking to somebody who studies formal logic, I'm not sure they would talk about scope in the same way that we do in computer science, but it helps me to think that, okay, lines 1 through 5, all in scope for me to use here. Lines 1 through 6, all in scope for me to use here. Since I'm outdenting with the CP here, the line numbers are going to be 4-7, right? Because that was my, I started with W4, and that implied W7 for this, right? W4 implies W7. That gets me out with my CP. And from this point on, I can't use lines 4 through 7, right? Here I've got 1 through 3 and 8. Here I could use 1 through 3 and also 8 and 9, but 4 through 7 are always out of scope for me. And here, look, I've decided to end with a CP or an IP, and I've outdented again. And now the lines that I would use if I use a CP or an IP would be 1 to 3 and 8 to 10, right? Everything except this 4 to 7. Here's a generic IP subproof. It's almost identical, except that what we do is, because we're doing IP, we assume, let's say we assume W4, and we get to false. That means when we outdent, we're going to conclude not W4, right? And again, with lines 4 to 7 IP. And there's just a summary of all the lines that are sort of in scope, right? Code block, think code block. Okay, so let's do a proof with another subproof. Let's just do another example, a real example, not sort of that outline thing. And the question says, prove the converse of A or B implies not B implies A. So this implies has the lowest precedence here, but what the heck is converse? Well, converse is just flip around the arguments to the implies, right? So what this is asking us to do is to prove this, okay? So this proof is about as nasty as you can get. It's actually a proof with a subproof and a sub-subproof, right? And you can tell that by looking at the indentation. But I wanted to give you this so that you can see sort of how you figure out what line numbers count for what different things. So this is not a proof I would ask you to do, but it is a proof that I would ask you to understand. And if I gave you this proof, I think you should be able to figure out what to put in on the right-hand side for the reasons. So let's see, we're trying to prove this implication, right? And so the outline of this proof, we can start by looking at this proof by just looking at line 1 in the very bottom, right? We expect it's going to be a CP proof, right? Because we're trying to prove that one thing implies another. So here's the one thing. And if we can derive the other in this proof, which it looks like we do, then we can outdent with a QED. And we'll figure out why it's just lines 1 and 10 in a minute, okay? But so we start here on line 1 with our premise. That totally makes sense. And if we look at line 2, we see that we are, I mean, we know we're in a subproof, right? Automatically because we indented. And subproof can only be CP or IP. Let's look at what this subproof is trying to do. This subproof is trying to figure out A or B, and we're assuming not A or B. So obviously this is going to be an IP kind of subproof, right? And if you look, here's the start of this proof. And if we just keep going along with the stuff at this level, right, at this sort of level of scope, we start with this. Ignore the indentation here for a minute. Look, from here, we derive false, so we outdent with IP. And we'll talk about how we got to these numbers in a little bit. So where were we? We started on line 1 with our premise. That makes sense. And then we got to line 2 with another premise, right? Because we were trying to prove the opposite of that with an IP. And we're going to do the same thing again. Now we're indenting again. So we have yet another subproof, right? This is our subproof we're starting. This is a premise, and it says for B. So we know that we're using IP again because we have not B here. We're trying to show B. So now let's just look at this little subproof piece for a minute, okay? And we're going to keep in mind that while we're in the subproof, every line above this, or sorry, the subproof, right? All the lines above this we're going to be able to use. So what do I do on line 4? Well, if I assume not A, then I can use modus ponens, my all-time favorite, right? I have not B, and not B implies A, so I can conclude A, right, with 1 and 3 in modus ponens. And I'm allowed to use anything above because I'm in the subproof, right? Next line, what have I got? I want to get from A to A or B using addition. And what did I say? Well, if I'm on line 4 and I have A already, and I can use the lines above, right, because I'm still in the subproof, I can just say A or anything, right? That's the addition rule. So A or B I get from line 4 with addition. Okay. And now I have A or B. And check it out. I also have not A or B up here, right, on line 2. And I can use everybody above. So I'm going to conclude false, right, by the contradiction rule, right? So from line 2, and line 5, I thought I was going to change slides, but I didn't. From line 2 and line 5, I have this contradiction. Okay, so far so good. So we're going to use IP and outdent, and everybody in that subproof is now out of scope. So lines 3 through 6 are what we used for this B, right? We assumed not B, and now we're using IP to figure out the opposite of that, right? And now we're just back into the subproof. But at this point, from this point on, I can't use lines 3 to 6. Those are out of scope now. Okay, so I have B, and remember that I was in this subproof up here, right? I was in just the plain old subproof. I'm trying to get to A or B. But if I have B, then I could conclude A or B. That's fine, right? So I do A or B just using addition, right? Because it's an or. You can add anything to or with the addition rule. So that's line 7 in addition, and that's okay. Not using lines 3 to 6, so I'm okay. And then check this out. I had not A or B up here on line 2. Line 2 is still in scope for me. And I have A or B here, so we're back to my maybe second favorite contradiction. So on lines 2 and 8, they're still okay, and they're still in scope for me. But now from this, I derived false, so I can use IP again and outdent. And what lines do I use? Well, I use everything starting with my premise for the subproof and going down to the end, except not the lines that are already out of scope, not the stuff in my subproof, because that's already gone, right? So what does it say here? It says it starts with line 2, it skips lines 3, 4, 5, and 6, and then I have lines 7, 8, and 9. So see on here, I say line 2, 7 to 9, IP. And now, boy, the main level of my proof, let's go back for a second. The main level of my proof is line 1, right? Line 1 still in scope. All this stuff is out of scope. But I can do the my QED, right? I can use CP, because what was I trying to show? I was trying to show that this implies that. And I started with this, and from this I derived that. So I can outdent with QED, right? And what am I using? Well, I'm just using 1 and 10. They're the only ones that are still okay for me to use. And now I'll show you that cool extra, right? For this one, we assumed A or B by so that we could prove it. Sorry, we assumed the not of this so that we could prove that, right? And we assumed not B so that we could prove B. So here again, just so you can see it in its hideous entirety, is the full example again. So go through this and just look at it step by step and make sure you understand, where does the subproof start? Now I outdent. What is no longer sort of in scope, right? When do I write stuff in braces, right? All this stuff, right? Just review and make sure that's clear to you. Okay. So let's just wrap this up with actually seeing why it might be useful. One of the things we can do is we can turn English statements into woofs, right? So for example, we could say that S stands for I eat spinach, and I stands for I eat ice cream, and L means I study logic, and P means I pass the exam. And G means I play golf, right? And so let's look at my sentence here. I eat spinach or ice cream. If I study logic, then I will pass the exam. If I eat ice cream, then I will study logic. If I eat spinach, then I will play golf. I failed the exam, therefore I played golf. Okay? Sort of crazy, but let's look at this. The first part says I eat spinach or ice cream. Well, look at that. I just have S or I, right? If I study logic, then I will pass the exam. Well, that's an if then, right? So L implies P. If I eat ice cream, then I will study logic. So I implies L. If I eat spinach, then I will play golf. S implies G. And I failed the exam, so I didn't pass it, right? So not P. All right, so these are all my premises. And this is the conclusion that I want to get to, which is, therefore, I played golf. And the question is, can you prove it? Now, for sure, you could prove it using just the inference rules that we have already. But it's actually way easier if you use these derived proof rules. So these are the ones that you see at the bottom of that sheet that we haven't done yet, right? And these are just very useful rules that you can prove using the basic inference rules to prove them, okay? And these are like the regular ones, not like IP and CP, in that you can also prove them using truth tables. So for example, let's try and take a look at modus tollens. Here is what modus tollens is. Again, I copied it up here. And you can kind of step through this and see that by the time I get to the end, it's true, 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 true. So it's a tautology. So I have proven this just using a truth table, right? What have I proven? This and this implies that, right? This and that implies that. Okay, so that's a truth table for modus tollens. So our derived rules will help us with this proof. So I've given us some, I've started up a sort of scratch area again that we can hand right onto. And let's just look at what we've got. We've got a bunch of premises, right? And I didn't copy what is, which is ice cream and what they all stand for, but you can look back at the slides and see. But these were all the premises that we got, and we were trying to prove G, right? So we're trying to show that all of this stuff implies G. So let's make this a little bigger so we have a little bit of space. And let's just take a look at what we've got. I've kind of given you a big indication that we're probably going to be using the derived rules for this proof. So let's take a look at what they are. If we take a look first at modus tollens, that says if we know an A implies B and a not B, then we have to know, we can conclude not A, right? And check it out, we have a not P here, and we have L implies P. Now, for real, the real way you do these kinds of proofs is you just kind of bang at them until you get an answer. And banging at them means, let me see, what do I have here? And what are the rules I can use, and try and combine those things. But I'm going to bang this time by looking at modus tollens first, because you've been watching this video for long enough already. So what I'm going to say is we can conclude, let's see, we can conclude not L, and we can conclude that from lines 2 and 5, that's a 5, using modus tollens. Oh, and we have not L now. I mean, I'm trying to get to G, right? And to get to G, I need to, right, G is the end of my proof. And look, I've got I gives me L and L gives me P, and I have a not P here, right? Which is what I used to do. The L gives me P, and now I have a not L. So maybe we should just try modus tollens again. Because it's, it's something we could do, right? So let's just try it. So now I can say, since I know not L and I know that I implies L, I can say not I, and that would be from lines 3 and 6, and modus tollens. And unfortunately, we don't have anything that takes us to not I, right, or to I. So we're kind of out there. But what do we have? Oh, well, look at this. We do have up here S or I, right? And if we know S or I and we know not I, then because you've sort of studied these rules, right, you have to kind of look at all these things and get a feel for what are the kinds of things I can do. And one of the kinds of things I can do is if I know A or B and I know not A, then I can conclude B. So we're going to use a disjunctive syllogism on this guy. So I'm going to have line 8. We can conclude S, right? And that's from line 1 and 7, and DS is our reason. And now I know S, and S implies G on line 4, so we are golden. I'm going to say on line 9, I can conclude G, and that's from, you know what, my favorite, lines 4 and 8, and modus ponens. And here you go. This is the neatly typed up version of the proof we just did.